Over the last couple of days, we've looked at ray diagrams for curved mirrors, and yesterday you looked at the mathematics of curved mirrors. If you think back to the ray diagrams that we drew a couple of days ago, you might remember some patterns that formed. One of the patterns that formed was real, virtual versus upright or inverted. Whenever we had a lens or a mirror, it didn't matter. We had a real image, it was upside down. If we had a virtual image, it was right side up. Do you need to remember that pattern? No. Is it helpful sometimes? Absolutely. It's helpful sometimes to remember that pattern. Real is always upside down. Virtual is always upright. What else do we see? Well, we had a convex lens, which is a converging lens. Then we always had a upright, smaller, and virtual image. When we had a converging mirror, we always had an image that was upright, smaller, and virtual. So if you have a converging anything, then it's going to produce an image that's upright, that's smaller, and virtual. So you can remember that. Or you can draw your ray diagrams and not necessarily memorize the pattern. But sometimes it's helpful to remember that pattern. What about that was convex. What if we had, diverging, convex mirror, concave lens, okay, produced diverging lens, diverging mirror, produced the virtual, smaller, and upright image. What if you had converging? Well, the pattern's a little less recognizable this time, but it still ends up being the same for mirrors as it is for lenses. If we start off with an object way out here, whether we're talking about lenses or mirrors, we produced an image that was, anybody remember this? Yeah, it's smaller, inverted, and real. Let's just take a quick look at this. First ray parallel down through the focal point, second ray down through the focal point goes parallel. The image produced is, in fact, as Austin said, smaller, inverted, and real. Now, as that object gets closer and closer to the mirror, the image becomes bigger. So the first characteristic is smaller, inverted, and real. Then it's same size, inverted, and real. Then it's bigger, inverted, and real. And then it's no image. And then it's bigger, upright, and virtual. Again, whether we're talking about a converging mirror or a converging lens, doesn't make any difference. Let's draw one more where we have our object right here that's really close. We predict that to be larger, virtual, and upright. Let's just double check it. First ray down through the focal point. Second ray this time is going to go up away from 2F, which, by the way, could also be called R for radius of the circle, or it could be called C for the center of the circle. We extend those two reflected rays, and we find that they form an image right here. Sure enough, it is upright, it is larger, and it is virtual. One thing that I want to point out, one difference that I want to point out, though, is that for mirrors, when you get a virtual image, it's always on the other side of the mirror. For lenses, when you get a virtual image, it's always on the same side as their object. So the characteristics are the same for lenses and mirrors, as long as you've got converging or as long as you've got diverging. But the side of the lens / mirror that you're going to find the image on is going to be opposite. That make sense? Somebody this morning asked me, like, how could you have an image on the other side? And I said, go to the bathroom. And so I made him walk into the bathroom and look into the mirror. When you look into the mirror in the bathroom, what do you see? Like, you see yourself, but where does it look like you are? Inside the mirror on the other side of that wall, right? You ever walk into a room, like maybe it's a dance studio, or maybe it's like a weight room, a gym, or wherever, and there's mirror from floor to ceiling? You ever see a room like that? And sometimes, I don't know if you've ever noticed this, but I have a couple times, when you walk into one of those rooms for the first time, you flip on the lights or whatever, your first instinct is like, wow, it's huge. And then you realize like 2 seconds later, oh, wait, it's only half the size, because it looks like it's twice the size because the mirror is reflecting the room, right? You know what I'm talking about? If it looks like it's twice the size, then the image that you're seeing in the mirror must be on the other side of the mirror, right? If it looks like the room goes way over there, then the image is going way over there on the other side of the mirror. So it's entirely possible to have an image on the opposite side. There's nothing physically over there, but that's why we call it virtual, because the rays don't really go over there, right? They virtually converge there. Make sense? All right, so what I do want you to remember is that the characteristics for mirrors and lenses are the same as long as you're dealing with concave, concave, or convex, convex. If you remember the patterns, that's even better. Okay? And if you remember how to draw both sets of ray diagrams, even better. But in the end, if you can get away with either drawing lenses or mirrors because the characteristics end up being the same. So you can take a little shortcut there if you want. All right. We took a look at some mathematics yesterday. Had two equations, just like we did for lenses. Except we're not calling it the lens equation, we're calling it the mirror equation. 1 over f is equal to 1 over do plus 1 over di. The magnification equation, hi over ho equals negative di over do. I'm going to go through this table real quickly, but it's going to be very, very brief. I'm going to say that you have three variables that go together first, f, do, and di. They're all going to be positive if they are real. If they're real, right? So it's real versus virtual that distinguishes between f, positive and negative for f, do, and di. Real focal point, real object, real image. By the way, when do we have a real focal point? If the lens or the mirror is converging. Okay, that would be a convex lens or a concave mirror. Now, what about hi and ho? Or ho and hi? They're going to be positive if they're upright. And they're going to be negative if they're inverted. The pattern? Well, maybe you want to remember this, maybe you don't. If you have an upright image, it will always be virtual. So you can identify a couple of things from one variable here. If you end up getting a positive hi, that means it's upright, right? But you also know that means it's a virtual image, so di would have to be negative. Sometimes you can do a nice little check with that, right? If you recognize those patterns, it's helpful in saying, oh, wait, my signs don't agree. Something's wrong somewhere in here. I should try this again with my 6 hours that I have to complete my exam. One final one, that was magnification. When should it be positive? Pretty much the same as the blue, right? Except that, well, assuming our object is right side up, then it follows the pattern for blue. But if our object is upside down, then it doesn't, right? Bottom line is, if the image and the object are both upright, then it's positive. If one's upright and one's inverted, then it's going to be negative. Okay, we had 5 questions, that you were working on from yesterday that you saw after your little written response test. Any of these questions you'd like to go over here, 1 through 5, on page 664? 5? I remember 5, definitely 5. 4? You know what, I want to go over 2b as well. I got 2b, 4, 5. Any others? Nope. Okay, 2b it is. It says determine the image distance, the magnification, and then the attributes or the characteristics. If we have a diverging mirror of focal length 5 centimeters with an object 10 centimeters from the mirror. Why am I circling that? Because what? Yeah, if it's a diverging mirror, it's a negative focal length. So let's write down those values here. My focal length here is negative 5.00 centimeters, and my object distance is 10.00 centimeters. I want to find the image distance di. I want to find the magnification. I want to start off by saying 1 over f is equal to 1 over do plus 1 over di. 1 over what? 1 over what? Brendan, 1 over what? What do I sub in here for f? Yeah. What you got to be careful of there is to not make it positive 5, right? Okay, it's a virtual focal point because it's a diverging mirror. Diverging lens would be the same. 1 over 10 plus 1 over di. What's the steps on my calculator here? What are the keystrokes here? Negative 5 what, Kessler? Good. Negative 5 to the minus 1. That's the same as saying 1 over negative 5, right? Now, how do I get the 1 over 10 over to the other side? Subtracting. So let's subtract 10 x to the minus 1. Answer? Is that my final? No? What do I got to do? I got to flip that over because that's 1 over di, right? We want to find di. So flip it over and we get negative 3.33. Now, this tells me directly that I have what kind of image? It tells me it's virtual. It tells me it's a virtual image. Because remember, f, di, and do are based on real or virtual, right? Now, indirectly, it tells me what? A virtual image is always, now this only works if you remember the patterns. A virtual image, Matt, is always good. A virtual image is always upright. So we can, in addition to saying that this is a virtual image, we can, by looking at this, say that it's an upright image as well. Now, this only works, you can only determine that if you remember the patterns. There's always another way. I'm just saying sometimes it's helpful to remember those patterns. What else are you looking for? The magnification? HI over HO, or negative DI over DO. Negative 3.333 over DO, which was 10 centimeters. What is that? 0.33, I think? Positive? Okay, what other characteristics do I have? Well, a positive magnification told me that it was, assuming the object was upright, the image must be upright. So I was right about this. Nice little check there, though, right? Because I did it 2 different ways. Bigger, smaller, same size? Smaller. Magnification greater than 1, bigger. Smaller than 1, smaller. So it's virtual, upright, and it's smaller. Now, you could have determined the characteristics or the attributes without even using an equation, right? How would you have done that? I mean, maybe you remember. What is it? Austin? Did you say it? Somebody said it. Kessler? I heard somebody say it. How could you determine the characteristics of this if you didn't do the math like we just did? It's your 2-word answer, Kelly. What is it? Ray diagrams. Good. Just draw your ray diagram. Or you could remember those patterns, right? Which some people choose to do. All right, next question we want to go over is number 4, I think. Concave mirror, that's good. Concave is converging, right? That is for mirrors. For lenses, it's diverging. Image characteristic, using a ray diagram and the mirror equation. I don't want to use a ray diagram. I want to use the equation. It was 4 that we wanted to go over, right? Yeah. So HO is 4.0 centimeters. DO, 15 centimeters. F is positive 5 centimeters. And we're not actually asked to solve for anything here, right? But I guess what I'd say is just, you want to do this. You want to do this graphically, draw the ray diagram. You want to do it mathematically, solve for some. Like get some. Tell me what you can get out of this. DI, right? The image distance. And you're going to do that, Kessler, by doing what? Yeah. We used to call it the thin lens equation. Now we're calling it the mirror equation. 1 over f is equal to 1 over do plus 1 over di. So we'll say 1 over 5.0 equals 1 over 15 plus 1 over di. There's few things in life that drive me crazier than when people can't do things like adding fractions. But in Physics 30, we have a trick. If you can't add fractions, we have a trick. We use our little calculator thing, right? We say 1 over 5, how do we enter that again? 5 to the minus 1. How do you take the 1 over 15 over, Justin? Subtract 15 to the minus 1. Flip that over. Gives me 7.5, positive 7.5. All right. What does that tell us? Tells me it's real, for sure, right? It's 100% real, for sure. If I remember the patterns, then I also know that it is upside down because real is always inverted. I'll put that in another color because you may not have spotted that one, and that's okay. We don't know anything else yet. Now let's get, now let's say m is equal to negative di over do. Negative 7.5 over 15. Inverted? Was I right? Yeah. What's the third one? Larger, smaller, same size? Smaller. You know that because magnification is 0.5, right? Good? Yep.
Could you also solve for the image height and then compare the two?
Yeah, absolutely. Absolutely you could, yeah. I forgot that you had the object height that given to you there is 4 centimeters. So absolutely. I think this calculation is a little bit easier in terms of the algebra rearranging, but for sure, if you solve for the image height, you would have found that it would have been negative, which would have told you that it was upside down, inverted. And you would have found that it was, the image height would have been 2.0, which clearly means smaller than the object. So yeah, that works. There's almost always more than one way here between, you know, at least one way to calculate, often two, and patterns and so on. There's multiple ways of getting these. All right, last one, number 5. Really good one here. Light from a distant planet is incident on a converging mirror. I like that it's converging. Positive focal length. Although I don't know what f is. The image forms on a screen 45 centimeters away from the vertex. It's the focal length and the characteristics. Well, I said that the focal length is 45. And I said that because, well, if this is our mirror right here, and we have an object right here, this object will produce rays of light going in every which direction, lots of them missing the mirror, but these ones hitting the mirror. Agree? Let's have the same mirror, but let's be further out. This produces lots of rays of light again, but most of them miss the mirror. These ones don't. What do you notice about those blue rays this time versus last time? They're what? Well, there's less of them because the ones that go at these big angles right here just skip the mirror, right? In other words, the rays of light that actually hit the mirror are closer to being parallel, right? The further away you are, the closer they are to being parallel. So if you're looking at a big star or a big planet, a big distance away from the Earth, the rays of light that go through the lens or strike the mirror and bounce off are going to be pretty much parallel to each other. Where do rays that are parallel to the principal axis converge? Focal point, at the focal point. Not where do the rays that come from the focal point converge, but where are the ones that are coming from something far off that are parallel to each other converge? The focal point. Now, these ones aren't necessarily parallel to the principal axis, so if they're parallel, though, they'll still converge at, above, or below the focal point. So in other words, if the image is formed on a screen 45 centimeters away, then that means the focal length is going to be 45 centimeters. Now, I'll tell you what. When I did this question first, that's not the way I did it. I actually solved this mathematically. I said that 1 over f is equal to 1 over do plus 1 over di. We're looking for f, right? di is 45. Okay. Here's a few quick easy questions for you. What's 1 over 1 equal to? 1. What's 1 over 2 equal to? 0.5. 1 over 3? 0.33. 1 over 4? 0.25. 1 over 5? 0.2. 1 over 1,000? 0.001. 1 over really, really big? Not big. 1 over really, really big is really small. Effectively 0. Right? Compared to 45, that's going to be 0. It's not going to be 0, but it's going to be close enough to 0 because 1 over 45 is my other number. So that makes f what? That makes f 45 centimeters. Now, what about the characteristics? I don't see anything from that, actually. It's converging, so it could be real or virtual. Upright or inverted. Say m is equal to negative di over do. M is, what is negative di here? Oh, negative 45, right? What's do? Really, really big. So 45 over really, sorry, negative 45 over really big is? Nope. Negative small. So what does that tell you, the fact that m is negative small? It's smaller than the object. Does that make sense? Doesn't a telescope make things bigger? You ever look through a telescope? Look at the moon through a telescope. Okay, let's say that your telescope has a big enough lens where you can actually see the entire moon. Okay? It's magnified, right? But you can see the whole moon. Are you suggesting to me that that's a bigger image than the object? When you look through the telescope and see the full moon, are you saying the moon is really smaller than the image that you're looking at? Of course the image is smaller. The image is smaller than the object. You can see it closer up, but it's still a smaller image. So the magnification should be small. What else does it tell you about the image? So it's right side up? Is it right side up? Kathleen? It's inverted. How do you know it's inverted? Because the magnification is negative, right? Is it real or virtual?
Real.
How do you know it's real? Because what? Because it's getting projected onto a screen, right? That tells us it's real. Real, smaller, and inverted.